6002X, as I mentioned earlier, is the first course in a typical EE or EECS curriculum, as it is at MIT. So before we start, I'd like to spend some time discussing where exactly such a circuits and electronics course and the content that it teaches fits within the grand scheme of things. We will start by trying to understand what is engineering. Well, engineering is the purposeful use of science, where science itself is the study of what is. In other words, it's a study of nature. With engineering, we are now focused on what we make of nature. It's what we build. It's how we can use science to help humanity. Okay, so then where does 6002X fit in? 6002X is about the gainful employment of Maxwell's equations, going all the way from electrons to digital gates and op-amps. As I mentioned earlier, just as engineering is the purposeful use of science or nature, 6002X is about the use of Maxwell's equations. Now, when you have nature, that is what is. So you can study nature, and that is science. You're not allowed to change anything. With engineering, you are looking to build cool stuff, things that can help humanity. And in order to build such stuff, we often abstract nature, or we abstract what is, into laws. And Maxwell's equations are laws that govern the behavior of one part of nature. And 6002X is about employing Maxwell's equations to build cool systems that can help humanity. Now, let's try to get a better handle on exactly what we mean by looking at how nature behaves, or at least nature as described by Maxwell's equations, and let's see how that will lead to building really useful systems that can help humanity. So let's put nature and what is on the left-hand side, and on the right-hand side, let's put down some of the kind of things that we may want to build that will help humanity. So, computer mice are an example. Cool devices like your iPad or your Razer phone are useful devices. Space shuttle, stereo systems, sonar, even Angry Birds. So let's see. So how do we take nature, what is available to us, and how do we build, as engineers, really useful systems? So we start with nature. That's what we are given. So what we could do is look at how nature behaves by performing sets of experiments. So we could perform experiments and build some tables. So as one example, in the area that we are concerned about, we can measure voltages and currents. So for various voltages, I can measure currents that arise from those voltages. So I could have 4 volts and so on and so forth. I can apply voltages to some material and measure the current that flows through those materials. In the same manner, I can collect tables and reams of data to characterize all kinds of parts of nature and have reams and reams of this data. So I could take reams of this data and somehow try to build those systems based on all those properties of nature. Now that is clearly a Herculean, if anything, ludicrous task. So what do we do? I mean, this is just too hard. And nobody sits down with reams of data looking at how nature behaves and build systems. What do we do instead? What we do as engineers is we start by building laws or abstractions that succinctly describe how nature behaves. So for example, I can take these measurements that I made of voltages and currents, and I can say, aha, I can describe certain materials that behave according to certain laws and write an equation such as V is equal to Ri, which is Ohm's law, that governs certain types of devices. Other phenomena are described by Maxwell's equations. And these equations, now, whether it's Maxwell's, Ohm's, or classes of other equations, think of these as succinct expressions or learning from those reams and rooms of data. So here, these equations can be thought of as abstractions for those tables of data. And just imagine a simple law like Ohm's law, V is equal to Ri, which you've learned about in your high school advanced physics courses. Now, in one little simple equation, V equals Ri can describe reams and reams of data that govern the behavior of certain classes of devices. Okay, so we have simplified our lives quite a bit. But still, trying to use Maxwell's equations to develop Angry Birds or to develop computers and so on is just a mind-numbing task. Just can't be done. So what do we do instead? So remember, we are engineers, and our goal is to build these systems at the end that will help humanity. So what we will do is we will make some assumptions that you will see in the rest of this lecture, and by making certain classes of assumptions, we will build what is called the lumped circuit abstraction. Now, in the lumped circuit abstraction, we have a set of lumped elements or discrete elements such as resistors, capacitors, voltage sources, inductors, transistors like the MOSFET switches, and so on and so forth. So now, rather than using equations and equations, we build some abstractions and build some discrete devices that we shall use in building systems. Now, we could take these simple devices and go ahead and build computers, but nobody does it that way. When you build a computer, such as a modern microprocessor, such a microprocessor might have 10 billion elements in it. There's no way we can sit around dealing with resistors and MOSFETs in quantities of 10 billion and individually build systems using that. So what we do is, again, apply the process of abstraction. Okay, we abstract out the behavior of collections of these elements, and the next abstraction that we will make in this course is the simple amplifier abstraction. Okay, we'll learn a lot more about this as we go on. This amplifier may have dozens, if not hundreds, of these lumped elements inside them, but then we will go and continue to work with those amplifiers, which are abstract conglomerates of a lot of these elements. So at this point, life can take a couple of turns once we build the simple amplifier abstraction. So one thing we could do from there is use that to build what we call the operational amplifier abstraction. And then using that, we can build even more complex systems such as filters. Filters are able to process data in various ways and give us a set of outputs that might suit our purposes in engineering certain classes of systems. Then we build the next level of systems, analog subsystems such as oscillators, modulators, RF amplifiers, power supplies, and so on. And then those would be used in systems like the space shuttle or phones and things like that. So that is one whole set of directions that we can take. Think of that as the analog direction. Now we can take a second direction that is along the lines of the digital abstraction. So in this world, we will make a different set of assumptions. And you will see that what we will do is, rather than look at a continuous set of values, analog values, we will simply look at dividing up all values into two discrete quantities, 1 and 0. And by doing so, we will build up what we call the digital abstraction. And the first set of components we will build in the digital abstraction are what are called gates. Following that, we will build even more complex logic, combinational logic. And then, using combinational logic, we will apply some time domain signals like clocks and so on, and build what we call clocked digital systems. And abstractly, these clocked digital systems will be used to build even more complicated and useful systems, such as microprocessors. So, for example, the abstraction we make is called the instruction set abstraction, or ISA, I-S-A. And the instruction set abstraction will allow us to build an even more complicated class of systems that are characterized by their instruction sets. So we can have the MIPS instruction set, we can have the Pentium instruction set, and so on and so forth. Following that, we will build another level of abstraction, trying to build systems using instructions in the ISA of a microprocessor is just way too complicated still. So we build higher level languages. And I'm sure many of you are familiar with languages such as Java, Python, C++, and so on. Following that, we build software systems or hardware systems such as operating systems and web browsers and things of that sort. And then we have the big combination where we take the subsystems we put together, both from the analog dimension, such as power supplies and so on, and pieces of computer hardware such as oscillators. And then from the digital side, we take both software systems and hardware systems like microprocessors and combine them. And after we combine them, we end up with very interesting systems like games and so on your handheld devices or the space shuttle, for instance. Now, what does 6002 cover? So 6002 will help you make the transition from physics and take you all the way into analog and digital subsystems. So 6002X will take you from physics laws, make the jump to engineering, where we will abstract these physics laws and properties into lumped devices, build the lumped circuit abstraction, and then take the one path on the analog direction, and build analog subsystems. And then we will also go down a fair bit down a digital path and take you all the way to primitive clocked digital components. And the reason we cover this amount of ground in 6002X is really to emphasize the point that the foundations of both the analog and the digital world are the same. Okay, the foundations are the same lumped circuit elements, and whose foundations are your basic laws of physics such as Maxwell's equation. And of course, the foundations of those laws is nature as you see it. So there you have it. This should give you a sense of the grand scheme of things in 6002X, and for that matter, in pretty much an entire EECS curriculum. So just to show you why this large map here pretty much covers the typical EECS curriculum, notice that a course at MIT such as 6061 will cover power supplies. A course such as 6004 or 6846 will cover computer architecture and parallel computing. A course such as 6002 will cover introduction to programming. A course such as 6033 will cover basic software systems. And there'll be many other more advanced courses that will cover further advanced components. Now, to get a sense of many of these follow-on courses, you can get a sneak peek of the material at OCW, OpenCourseWare, or as over the next few semesters, we shall make many of these courses available on MITx as well.